The source of the data on this chart is EIA data, Energy Information Agency, which is a part of the federal government, which we've used several times throughout the class, and I consider this to be very credible data. This shows you how energy is used, and for the various sectors of the U.S. economy, what types of energy it uses. The thing I want you, and it's worth spending some time looking at all the small numbers on the charts, but the main takeaways I want you to get from this is, largely in America, transportation is powered by petroleum. And for the most part, the vast majority of petroleum, crude oil, is used in the transportation industry. Natural gas has a more balanced portfolio in that it both heats American homes, but it also is increasingly being used to power America through electrical generation. Now, as opposed to coal and nuclear power, which are largely used to power America through electrical generation. Then you see the renewables, although they have a little bit of a balanced portfolio, still for the most part, they're being used to power America. Some of it's in the terms of residential solar, which again is actually a very, very small percentage. It's actually not nowhere close to being even 1%, but in terms of its capacity, that's where it is being used. So that's why we almost can segment the market into two areas. One is transportation versus electricity. So now let's look at transportation. And if we're going to talk renewables, and specifically battery-powered vehicles, you get into the idea of power density. So now I'd like to give you a comparison. Both of these data comes from the manufacturers on the Toyota Camry, on the Tesla Model 3, which in terms of size and appointment levels, they're good analogs. What you want to see is that the car, the Toyota Camry, is much lighter than is the Model 3. And the statistics I'm quoting for the Model 3 are for the long-range version, which is the version that Tesla reports can achieve a highway mileage of 310 miles. And again, that's a manufacturer's number, so you know it's really not going to go that far. But likewise, 590 miles is also Toyota's number based on EPA testing of the fuel. For what it's worth, the engine in the Camry weighs about 360 pounds. There's not enough information yet available on the Model 3 to figure out exactly what its battery weighs. My guess is the battery alone weighs about 1,000 pounds. And you can see that's why there's a weight difference between the cars. You save a lot of the weight of the engine, but you put in a very heavy battery. And you can see even on this long-range Model 3, which incidentally, to buy the larger battery that gives you the additional 90 miles of range, adds $9,000 onto the price tag of the car. So this is a $44,000 car on the right. But you can see from a range standpoint, it's still very challenged. If you're trying to take a highway trip, that's going to be a problem. And that's why I say until unless the power density and the recharging of the batteries significantly improve, long-range transportation is going to be very problematic for any electric vehicles. And again, this just has to do with the sense of power density. We'll talk more about batteries a little bit later in the discussion. So now let's talk electricity. Since we kind of segmented the market, there's transportation and then there's electrical generation and electrical usage. What does electricity look like in its demand? I'm going to show you a series of charts about how electricity usage varies. The data on this chart is from ERCOT, and I'll tell you who ERCOT is in just a minute, showing you what a hot day in August in Texas really looked like. Part of what you want to walk away with is at the peak points of the day, you needed almost twice as much electricity as you did during those very early morning hours when electrical demand was at its lowest. Here's a more generic chart that explains to you the impact of heating. So you can see on very hot days, during that peak heating period, you need a lot more electricity. And this is a comparison between an 83-degree day versus a over 100-degree day. Again, big variations across the day. And this explains to you how electrical generation is typically done. One of the things I didn't realize when I first set about learning all this is supply and demand in electricity always has to be kept in balance. And I'll tell you about the agency in Texas. that does that in just a minute. So you have what's called the base load plants. These are plants that are almost always on. These tend to be your large coal power plants and also the nuclear power plants where you're not bringing them up and down. They're like a huge cargo vessel. You put them on course and they are on course on that speed all the way across the ocean. So they form that base load that you're never trying to take offline. And then you have another series of power plants that are brought up for relatively shorter periods of time. And you see the peaking plants on the bottom, and this is where the difference between what's the weather going to be today. Is it going to be really hot or is it going to be really cold? Then we're going to need that peaking capacity. You always, if we go back again to that model of, we always want electricity to be available. Our standard in the United States is 100%. It's always got to be available. And because of that, you always have to have generation capacity to be able to turn on and turn off to meet that. The agency that manages that in Texas is called ERCOT. You see what the abbreviation stands for on the bottom of the chart. Texas is very unique. On this chart, you see what seems to be lots of different agencies. I'm going to show you in the next slide, though, that there's really only 3 interconnected grids in the United States: the Western, the Eastern, and ERCOT, which is largely Texas. Doesn't include all of the Panhandle and very West Texas. Incidentally, we're going to compare this much later in the discussion to Germany. And in terms of land mass, ERCOT's land mass is about the same as the German electrical grid, but in terms of the population served, the German electrical grid serves about 3 times the population. Here's where I showed you there's the Western grid, the Eastern grid, and then there's ERCOT. The dark lines on this chart show the longer range interconnects that are available, which shows you that for the most part, electrical power is generated fairly close to home. In the case of ERCOT, it's all generated inside Texas because there's actually very little interconnects between the ERCOT grid and the Western and the Eastern grid. So if we have a problem in Texas, it's largely up to Texas to solve it because we don't have the interconnects into the broader world. It's a political story as to why it developed that way. It's kind of interesting, but we'll just leave it at that for now. So let's look at Texas. Texas looks like, in terms of its electrical generation, and the source for this data is the EIA, where America is headed. And what I mean by that is you can see that coal usage is down quite a bit, a lot of natural gas usage, and also a lot of wind usage. Percentage-wise, not the greatest wind usage, but in terms of the actual amount of wind usage for a state, it is a tremendous amount of wind. And so I really think Texas is a great analog, and ERCOT is a leader in integrating the renewables into the grid and then making them available. Now, this is one of the things where I want to talk about this dispatchability for just a minute. It's a very important concept, and we'll tap on it. You're going to see lots of announcements like, for example, in Germany, there was an announcement that on this day in March or this day in October, renewables provided 100% of Germany's electrical needs. And that's a true statement. And you'll see the American Wind Industry Association that will say, on this day in March or this day in October, Texas, wind provided 98% of the electrical needs in Texas. And that's true. But what's the situation? They picked a date when A, wind production tends to be at their greatest, and B, electrical use is at its lowest. And so you can get a misleading picture when you look at when your thing does the best and the overall demand is the lowest, which again, remember, we always expect the lights to come on. We always expect the air conditioning or the heat to come on. And because of that, you don't plan for the best day. You have to plan for the worst day. So I've laid the groundwork, and now we're going to step into the discussion of the actual technologies.